4 cards are drawn from a well-shuffled deck of cards. What is the probability that all 4 are black? So we're going to draw 4 cards, and they're talking about black cards, so I'm going to partition the deck into black cards and red cards. Half the cards are black, half the cards are red. But they want us to draw 4. But we don't care about what order we draw them in. You're just going to get 4 cards out. You don't care that this one was the first you drew, and this was the second, and this is the third, this is the fourth. You just draw out 4 cards and look at them. They're distinct. There's only 1 3 of clubs in the deck. There's only 1 7 of clubs in the deck. There's only 1 queen of hearts in the deck. So those are distinct cards, and you don't care about order. That tells you immediately that you're dealing with a combination, because order does not matter and the objects are distinct. But also, by the basic probability principle, we also know that to find the probability of getting all 4 black cards, we simply have to count how many ways we can draw 4 black cards and divide by the number of ways we can draw any 4 cards. Remember, probability is always what you want over any possibility. So the probability you get all 4 black cards is the number of ways to draw any 4 that are all black over the number of ways to draw any 4 cards, don't care if they're black or not. And as we said earlier, the numerator and denominator of that basic probability principle both can be calculated as combinations, because in neither case do we care about order. So what about the black cards? I'm drawing 4, so obviously that's a 4, but if I want all 4 cards to be black, I can only choose from the black cards, and there are 26 of them. So as you practice these, think about, as you're working them, how this all plays out. The number of things you're choosing is always the smaller number, which is on the right. What you're choosing from is the larger number, which will be on the left. So the number of ways to draw 4 black cards from an ordinary deck of 52 cards is a combination of 26 things taken 4 at a time. And it's a combination because order doesn't matter. But once you see that, the denominator should be really easy. The denominator is the number of ways to draw any 4 cards. So I still will draw 4 cards, but this time they don't have to be black. They can be black or red, so they can be any card. Well, there are 52 cards in the deck, so the number of ways to draw any 4 cards when I don't care what color they are is a combination of 52 things taken 4 at a time. And when I do those 2 calculations, I'll get a fraction, and that fraction is the probability of getting all 4 black. So let's do that. Now luckily you have a calculator that can do all the hard work. So what you do is you enter 26, then remember the combination is shift 2, then you enter a 4, and to evaluate you press equal. And when you do that, you will get 14,950. And now we just do the same thing with the denominator. The only difference is that we're entering 52. We still do shift 2, then we enter 4, and finally we press equal. And that comes out to 270,725. And I do want to say one thing about this. Sometimes the problem asks you to round something off to a certain number of decimal places or leave it as a decimal. This problem does not do that. Whenever it doesn't say, the default is to leave it as a fraction, but it has to be completely reduced. Now this problem poses somewhat of a challenge because the numbers are so big. I can tell that it's not completely reduced, but to actually do the reduction may not be quite so easy. So I'm going to suggest a strategy, and I know that it's just rote, but you have to take some time to practice this, because you'll see these on your homework like this, and going through all of this and getting to this point will not get you the correct answer if they're expecting a reduced fraction. So no matter how tedious it is, you need to spend some time making sure you can do this. And here's my strategy. I know that they want us to reduce this fraction, but those are really big numbers. Here's my suggestion. We're dealing with a standard deck of cards, so when I'm looking for common factors of these really, really big numbers, I usually start off with numbers that relate to a deck of cards. For example, I might try 52. There are 13 cards in every suit, so I might try 13. There are 4 suits in the deck, so I might try 4. So it's just a strategy when I'm dealing with really large numbers. Now these numbers happen to be very large. I might try this because I know I'm working with a deck of cards. Well, let's see how this strategy pays off, see if it really works for me. I tried, and you'll have to take your calculator to do this, but I took my calculator and I tried to divide. Remember, it has to work with both, but I just picked out the numerator, 14,950, and I divided it by 52 on my calculator, and it doesn't work. Well, if it doesn't work with one, I don't really care if it works with the other, so I just skipped 52. That didn't work. So then I'll try 13. So I take my calculator and I divide 14,950 by 13, and since it worked, I also divide 270,725 by 13. And believe it or not, it actually worked. When I divided 14,950 by 13, I got 1,150. So that tells me that 14,950 is equal to 1,150 times 13. And then when I divided 270,725 by 13, I came up with 20,825. So that tells me that 270,725 is actually 20,825 times 13. Now I know this is tedious, but if you want to get the answer after having done all the other work, you have to take the time and do this tedious part too. So what I noticed is those 13 cancels. So now I've reduced it down. The question is, will it reduce any more? Well, one thing I noticed immediately, if a number ends in a 0 or 5, it's divisible by 5. I've already tried a fairly big number, 13, and the 2 remaining numbers now aren't too terribly big. So if I just notice that since 1150 ends in a 0 and 20,825 ends in a 5, I can immediately see that I can take a 5 out of each one. So I just sort of noticed that as I was looking at my first reduction. So I took advantage of that. I divided 5 into 1,150 and got 230, and I divided 5 into 20,825 and got 4,165. Now remember, I'm doing these divisions on my calculator. Not hard to do. But what I've done now is I've reduced it again because the 5's divide out. What you might notice, though, is that 230 ends in a 0 and 4,165 ends in a 5, so that means that they'll both divide by 5 again. So if I take 230 and divide by 5, I get 46, and if I take 4,165 and divide by 5, I get 833, so the 5's will divide out again. So at this point, I have 46 over 833. And you might say, well, am I done? Once at least one of the numbers gets fairly small, most of your work is done. What I realize is that 46 is just 23 times 3. So unless 833 has a factor of 23 or 3, I'm done. So what I do is I'll just take 833 and divide it by 23. I see that doesn't come out even. Then I'll take 833 and divide by 3 and see that that doesn't come out even. So if none of the factors of the numerator will go into the denominator, that means you've completely reduced the fraction. So now I know that I'm done. So the probability that if I draw 4 cards from an ordinary deck of cards that all 4 come out black is 46 over 833. And they asked me to do this as a fraction by implication. The default is fraction. If they want you to do it as a decimal, they will tell you that. But if you do have to do it as a fraction, you have to completely reduce it, and you have to sometimes go through this tedious work. So no matter how tedious it is, If you want to get credit for the problem, you need to take the time and do that.